Okay, so we are looking at hydraulic plate design for distillation column. So objective is to find out column diameter and height of column. Now while doing this, we check weeping. There are criteria which tells you that whether sweeping is there. Then we checked out whether the tray spacing is correct. There is criteria to check out this. Then third, we check out the pressure drop which we assume, is it correct? Fourth, we check out the flooding which we assume, is it correct? So this four things are different criteria is to find out, and then if this is all four are okay, then we say our design is appropriate. Now to start with, we start with a distillation column. This is a typical distillation column is. There is a condenser on top, a reboiler in bottom. Now we design first this with well-known Mcabe Thiele method. Okay. Now to design a column, what is required first is you require liquid and vapor flow rate at a rectifying section and at stripping section. Now the typical way what is given is you have been given flow rate, you have been given XF, you have given XD, what is expected, you have been given XW, what is expected in the bottom. Now what we have this equation F equal to D plus B. D is a top product, B is a bottom product, feed, F is a feed. There is another equation, basically component balance. So this will, so there are two equations, two unknowns. So you can find out D and B, and then you can proceed for a Mcabe Thiele method. So just like a revise of how do you have a Mcabe Thiele method. So first you have XY plot. This is X, liquid composition, mole fraction. This is Y, mole fraction. Okay. So you first look at a feed point. You look at a feed slope. Okay. Here you look at XD distillate. This is for bottom, and then wherever this meet the curve, you draw a line which will give us a minimum reflux ratio RM, and we are aware the actual reflux is normally 1.2 to 1.5 times minimum reflux ratio. Now with actual R, you find out new operating line, and then you find out number of stages. Okay. Now a slope of top operating line is L by V, which is liquid and vapor fluid in the top section. Now slope of bottom operating line is LW and VW, a liquid and vapor fluid at bottom section. So you know the slope. Now there are equation V equal to L plus D. So D was known from top. L comes from reflux ratio is L by D. So if D is known, L can be known and V can be known. Whereas in bottom, if you look at, this is LW, this is B, and this is VW. So balance is, what is coming in is LW, what is going is VW and B. If you look at the component balance, it is, I'll write XW dash because this and SW is different. VW YW dash plus B into XW. So what is known here? B is known. Now you know the YW dash is in equilibrium with XW. So you have X, Y, T data. From this you can find out respective YW dash for XW. So XW is known, YW dash is known. Now there are two equations, two unknown. So you can find out LW and VW. Plus you also know a ratio of LW and VW, which will make you find out LW and VW. So what we have finally? We have VL at top section, and we have VW and LW at bottom section. Stop.